Thank you, Juergen. And yeah, great to be here this morning. And I think everyone sort of feels that this is a real bit of a turning point we're at in regards to the journey of how we're looking at energy transformation. So what I want to do today is talk to you a little bit about the economics behind solar as well as battery energy storage for off-grid mines and what we found, what the actual drivers are behind this. So first of all, just looking a little bit at the bigger picture here, and I think the theme seems to be really about that energy transformation in the context of incremental hybridization. I think this term is sort of using the fact that over time we want to look at how we can introduce renewables step by step into the mining operation in order to be able to get to a point where it's not the diesel anymore that's a primary source of energy, it's actually the renewables then. So I will do a brief introduction into ABB and our history of what we've done in microgrids for the last sort of 27 years, and then really look at the technology that allows us to increment the penetration levels over time, and then go into the deep dive around economics and what we found from the modeling. So briefly, ABB is a power and automation technology company. We're operating really across sort of three main sectors: utilities, industry, transport, and infrastructure. And the interesting thing about microgrids is they really have a role to play in each one of these segments. So it's not just utilities, it's industry as well that's starting to look at how we can actually change our energy mix, as well as in transport and infrastructure around rail, as well as commercial sort of buildings. Looking at ABB Australia, briefly, we're about 1,400 people based in all major capital cities of Australia. And like Adrian mentioned, we've got the Center of Competence for Microgrids, meaning the R&D, being the lead center globally here in Australia, with a team based in Darwin as well as in Melbourne. Okay, so let's have a look at the history. Microgrids are not new. They're actually part of our journey, how we started to introduce first wind and then later on solar into off-grid systems. So we actually started in 1990 in the Northern Territory with adding storage systems to existing diesel power stations in order to avoid the start of the next generator and do some peak lopping. From there, in 1998, we built the first wind turbine in Denham, being connected to the Denham power station, which is an off-grid system as well, very close to the proposed mine we just heard about. And from there onwards, we developed a few more wind diesel systems and then moved into solar diesel. So as you can see, as the renewable energy technology like wind became more economic and then solar afterwards, we picked this up and started to integrate it with the diesel power stations. And lately, you've heard about this is the Grasser mine, so where ABB supplied the solar inverters, battery inverter, and integration technology to integrate this into what we've heard is operating today. So we've done this in Australia, but we've done it globally in a number of places as well. There's about 40 microgrids operating successfully now that we've put there, and they range from places in Alaska, for Kodiak Island, where you're looking at a 20 megawatt hydro combined with wind as well as diesel and storage, down to the other end of the earth in Ross Island, where we also build diesel systems. So quite diverse, and I think this is sort of what we've seen is that each microgrid is different, and we need to look at how we do the business cases and how we actually come up with the right economics. So briefly about microgrids, we see both systems appear now. So these are the grid-connected microgrids versus off-grid systems. And fundamentally, what we're finding is that the technology underlying the off-grid microgrids, as well as now the grid-connected ones, is pretty much the same. The grid connection is just another source of energy that can be utilized, but may be there or may not be there. So going forward, always a lot of discussions in NM are about how the networks are changing, and microgrids will play a very important role there, not just behind the meter, but in front of the meter as well, to provide ancillary services into the networks to allow the transition to happen. Okay, so let's look at drivers. Let's look at motivation as to what are the goals that different microgrid operators want to achieve. In the mining context, on the left-hand side, as operational goals, we heard a lot about, we're looking at fuel and energy cost savings, CO2 reduction, but also very much an uninterrupted power supply, meaning a very high quality of supply that we really want to achieve. On the right-hand side, we then have certain functions. We call them 8 S's. So these are actually 8 functions that we can provide with various technology in order to provide stabilizing of networks, provide, for instance, the ability to operate standalone. So standalone simply means for us that we turn all diesel generators off and only run with the wind and solar to provide the power into the network. But there are other aspects around, for instance, peak shaving, or making transitions from a grid-connected system into an islanded system as well. So technology-wise, it's about integration, and it's about being able to put all the different parts together. So we focus, if you look on the top left-hand side, integrating renewable energy together with the conventional power that most of the time is already in existence. Then on the top right-hand side, it's about storage and stabilizing. Stabilizing comes first, meaning we need to be able to ensure that any fluctuations or changes in the network can be smoothed out. And then secondly, it's about storing energy, for increasing the penetration levels. And then in the middle, you see the microgrid control system. So that one is really about bringing all the pieces together and then automate and optimize to get the outcome that we want. And this is combining together with those consulting services, because unless we can model a system very well up front and know what the performance is, it's going to be very hard to make an investment decision and make this bankable as well in regards to the performance and the outcomes. So what have we got as an options? We talked about incremental hybridization. What's the starting point, and what are the steps we can take to move towards a higher penetration output within those mining operations? So quite simple. First of all, there's 2 terms that are getting used. If you look at the one term, we call it energy contribution, which really reflects the fuel reduction we can achieve. And the other term is power penetration. So this is really the instantaneous output of the wind or solar against the load. And the peak penetration will always, or the peak power penetration will always be higher than energy, because that actually determines how much integration and how much stabilizing we have to introduce. So let's have a look at it. The very first line simply talks about installing solar with the existing power station. No integration, no control. Very simple to do, and possibly a first step. However, the downside is we might only get to 7 or 10% of fuel reduction overall, but a good starting point. Next, if we are able then to integrate simply the diesel together with the solar PV, we might be able to get to, say, 10 to 15% in order to increase the penetration levels, simply because the 2 devices are talking to each other. Next is to look at now technology that's available around, for instance, cloud forecasting. So cameras that look at cloud prediction, and they really help us to simply ramp down the PV before the clouds hit, and therefore avoid this step load in the generator that might have to pick up the loss of the PV, and therefore make a much smoother transition. But again, it's only getting us, say, to maybe 15 or 30% in order to be able to offset more fuel. The real change comes along when we look at introducing then battery energy storage systems to stabilize. So this means when we put storage with it, we can run, say, during daytime for solar, up to 100% only on the solar, together with a storage system. And if we get the cloud cover come in, the storage system will discharge and then may bring a generator online automatically. After we've done the ability to turn generators off, it's then a matter of maybe through load control to combine better shifting of loads from nighttime to daytime. And then further down, which is economically doesn't make a lot of sense today, but you simply increase the storage size in order to store more of the daytime energy of the solar and then discharge at nighttime. Briefly, the 2 main technologies behind this that we apply from an ABB point of view. One is the control system. We call it Microgrid Plus. It's a vendor-independent integration system or platform that allows us to work with brownfield sites, different generators, different models, different OEMs. Same on the solar inverter side of things. This is a distributed system that we use in order to, again, incrementally add step-by-step more renewables as well as more storage to it in order to get to those higher penetration levels. So that's one technology. The other one is the stabilizing/storage system. It's a containerized system that allows us to become the reference in a network. So we refer to it actually as more like a generator than a storage system, because it has got functionality inside that creates the grid reference and behaves dynamically like another diesel on the network. Therefore, we can turn diesels off and only run them with the storage system. Okay, so let's dive now into the economics and let's have a look at a business case. We've done a number of modeling scenarios. We used Homer Energy. We worked with Homer in Colorado quite closely to work through a range of these different scenarios to get a feel for where are we today, what are the sensitivities, and what does it actually mean going forward for various options. So we picked an arbitrary mine. We said it's a gold mine, with about 5 megawatt average load, 6.3 megawatt sort of peak demand. And we were looking at saying running 6 times 1.2 megawatt diesel generators. The business case is based on a fuel cost of $1 per liter, solar installed in the order of, say, $2 per watt peak, and then the cost of capital 11%. Now you're going to say, oh, hang on a second, that's totally different at my place, and that's probably very true. However, it's about working through the sensitivities and understanding for each side what are my input parameters and what is my optimized configuration of the site that I should actually deploy. So we ran 4 different business cases. Starting on the left-hand side, business as usual. On the left-hand side, we've got the diesel power station. We're running, say, up to 6 generators supplying the load, but 1 generator is always kept online for spinning reserve as an operation reserve, just in case 1 generator drops offline, that we don't obviously cause a blackout, that the other ones can pick it up. So that's our reference if we're looking at an NPV calculation, and we've done this over 10 years. The next quite interesting solution is not to start necessarily with renewables, is simply adding storage to the existing diesel power station for spinning reserve. What does it mean? It means we can turn 1 generator off, have the storage instead, and if we see a loss of a generator or an increase in load or just a peak, the storage system will kick in, discharge, and then if the peak goes away, we don't have to start another diesel, but in the event that the load has increased, we simply start another diesel. So here, there's a business case, and I'll show the numbers in a minute, that simply looks at spinning reserve with a diesel generator to create a return on the investment. The next case along is the one where we just simply introduce an PV solar with the diesel, and depending if we use cloud forecasting or not, we may be able to turn generators off, but even if we don't, we still will see we get a fairly good return. And then the number 4 is where we combine both technologies, that's the storage as well as solar PV, into an existing site, and that allows us, again, to push up to the point where we can turn all diesel generators off. Cool, so what do the numbers look like? In the same order now, on the left-hand side, starting with the base case, we're having a fuel consumption in the base case of about 11 million liters, and the levelized cost of energy is in the order of $300 per megawatt hour. Now, purely bringing the battery system with it for spinning reserve reasons, it's not a great saver in fuel. However, it will, from an operation, OEM, and efficiency point of view, reduce levelized cost of energy and provide quite a good return on the investment. Next come along is the diesel and solar PV option. Here, we're looking at about a 15% reduction, in fuel, and it does create a lower levelized cost of energy down to $289, dollars per megawatt hour. And the real big change again comes along when we're combining solar with storage. Here we're now looking at a reduction of 28% in fuel, and that allows us to get the cost of energy down to $273 per megawatt hour. Again, there's sensitivities behind those numbers, and those sensitivities I just want to explore a little bit more now. So most of you know that every site is different, and the key sensitivities that we found that we need to watch out for or we need to take into account is the number 1 thing, so it's actually fuel cost. And the volatility of the fuel price going up and down is one of those key drivers why, to get a more stable energy cost, one would start to opt into using renewable energy in this case. I go a bit more into the numbers on the next slide, but just visually to see fuel price is the biggest sensitivity if it comes to design of the system. The next one is the solar PV price installed. Obviously, doing this in a remote part of Australia, the costs are a lot higher compared to some of the numbers we would have seen, lately. However, there are still cases we can clearly see where it makes sense to go ahead and install a solar PV. last not least, it is location about solar radiation, about the resource, how much we can actually convert of the solar energy, then into electricity. And last but not least, the capital cost, say, of the storage system plays a role, but doesn't actually play such a strong role as one would maybe expect. So, looking a bit more detail, what this slide is trying to demonstrate is that on the left-hand side, we see how the solar PV price as a sensitivity across the bottom, as well as diesel price across the y-axis, leads to different system sizes and system configurations. Meaning, if we look in the top left-hand side, which is one extreme, which is really very high fuel price and very low solar PV cost installed, you find that then the storage size, as well as the solar PV size, gets fairly large. The same if we move across in the middle, it just means we could see up to 60% fuel cost reduction if we were in this corner where we've got very high fuel and very low solar PV price installed. And it could mean our EBIT, as in our cost to operate from an energy point of view, means a 24% reduction in levelized cost of energy. Obviously, looking in the other corner, on the bottom right-hand side, the numbers are a lot lower. However, they're still positive. They still mean you will get a return and you will reduce your cost of energy in the system. So the basic message here is, every site's different, got to evaluate where we are, what we're trying to do, and that really leads then to a conversation about what's the right way forward in that incremental hybridization of the mine. Cool. So looking at where are we today and where we're going to go. So today we have demonstrated from a technology point of view, we can get to 30-50% fuel cost reductions, not a problem. We've done this in a number of sites now, and it's not a technology question, it's an economic question. If you look at the forecast now of solar PV installed, as well as storage, those cases will only improve over time. And we're finding now through the conversation and early engagement is how you get the best outcome for what makes sense for your site. Okay, so in summary, technical integration we've demonstrated we worked on. I think the falling cost will help us to make this happen. Commercial integration, as we heard now, is the key to get good innovative models together between APPs, off-takers and so forth, how this best works. And it's that single point of responsibility from a warranty and technology point of view that will again drive costs down and manage the risk by those, that can actually do it the best way. And then last but not least, it's really the ability to do both greenfield sites as well as brownfield sites in order to start the journey as to how we can get to a much greener, running of those mine sites. Thank you very much.